In a clean room in Sunnyvale, California, there's a chip the size of a dinner plate sitting inside a refrigerated rack, doing in 1 second what 60 of Nvidia's best GPUs take a minute to finish, while drawing a fraction of the power. You've probably seen the photos, but most people miss why it actually works. It's not about size, it's about killing the memory bus. The obvious assumption is that the bottleneck is raw compute speed. It's not. It's something more mundane and harder to fix. And once you see it, you can't unsee it. Because the way we've built AI hardware for the last decade is quietly hitting a wall. Not a software wall, not a model wall, a physics wall. Every AI chip ever built has the same architecture. Compute on one side, memory on the other, a bridge connecting them. That bridge is called the memory bus, and crossing it, trillions of times per second, is where most of the energy in AI actually goes. The memory in a modern AI GPU is called HBM, high bandwidth memory. It's stacked vertically in layers, sitting physically beside the chip, connected via an ultra-fast silicon interposer. It's a genuine engineering achievement, and it still has a fundamental problem. It forgets. The charge holding each bit leaks away in milliseconds, so it has to refresh itself constantly just to remember what it already knows. The processor is the fastest mind in the room, but every piece of information it needs is across the hall. Shout, wait, read, send back, shout again. The processor isn't slow. The hallway is. In a large language model, more than half the energy doesn't go to computation. It goes to moving data. The chip isn't thinking, it's waiting. Scale that to a real deployment, and the hallway becomes a highway. At a certain point, adding more GPUs makes inference slower, not faster, because the coordination overhead compounds faster than the compute helps. Everyone in the industry knew this. Nobody had an answer. In the 1970s, the answer was simple: make transistors smaller. It worked like a law of nature for 40 years. Then the heat arrived. Pack transistors too tightly, and they generate more heat per square millimeter than rocket exhaust. Chips melted. The answer was parallelism. Stop making one core faster, build hundreds of simpler cores. That gave us the GPU. It powered the first decade of AI. Then power became the wall. A single training run today can consume as much electricity as a small city uses in weeks. Microsoft restarted a nuclear plant. Google is funding new reactors. That infrastructure spending doesn't touch the underlying problem. The same bottleneck remained. Inference cannot be parallelized the way training can. You cannot predict the next word until you finish the last one. So inference is fundamentally limited by one thing: how fast data crosses the gap between compute and memory. The tool that built AI is the wrong tool for the era AI has entered. Every chip starts the same way. A silicon wafer, 300 millimeters across, gets printed with transistors, then cut into small squares. Every chip the size of a postage stamp. There's a reason they stay small. Wafers have defects, microscopic flaws where transistors fail to form. On a small chip, one defect ruins one chip. On a chip the size of the entire wafer, every defect is catastrophic. This is why wafer-scale computing was studied since the 1970s and abandoned every time. Gene Amdahl's Trilogy Systems tried it in the early 1980s, spent hundreds of millions, and failed. A company called Anamatic later commercialized Wafer-Scale DRAM in 1989. It technically worked, but flash memory crashed the market before it could survive. The problem wasn't just ambition, it was yield, economics, and timing, and nobody had solved all three simultaneously. In 2016, a team of veterans from AMD and other leading firms decided to find out whether impossible was still true. 15 months, $8 million a month. One day, they powered it on. It worked. The Cerebras WSE3 has 46,225 square millimeters of silicon, 58 times larger than Nvidia's flagship GPU. The wafer is made up of 84 independent die, each containing over 10,000 compute cores. Those cores are tiny. A GPU core is roughly the size of a grain of rice, a Cerebras core the size of a speck of dust. That fine granularity is what makes defect tolerance possible at this scale. Cerebras solved the yield problem not by eliminating defects, but by designing around variance. Every wafer ships with redundant spare cores built in. When the chip powers on, it scans itself, finds every defect, and activates a spare in hardware. What ships is not a chip with 7% broken. It's a chip where redundancy absorbed the variance. All 900,000 advertised cores are active in every chip shipped. Using a process called cross-reticle stitching, TSMC etches continuous connections directly across the die boundaries during lithography, treating the entire wafer as one unified device. On a GPU, memory is HBM, stacked, fast by conventional standards, but still external to the compute fabric, still across a bridge. On this chip, memory is SRAM, woven directly between the cores. No refresh cycle, instant recall, and it isn't beside the computation, it's inside it. The result is 21 petabytes per second of on-chip fabric bandwidth, orders of magnitude beyond any GPU, even accounting for the difference in how that metric is measured. The bottleneck that defined AI hardware for 15 years does not exist inside this architecture. Third-party benchmarks show Cerebras delivering up to 20 times faster inference than Nvidia's H100 on Llama 3.1 and more than double the speed of newer Blackwell systems on some models. The performance advantage is real, but the business and technical risks are just as real. Every Cerebras chip is manufactured by TSMC in Taiwan with no backup fabrication line. Meanwhile, Nvidia has spent 15 years building CUDA, the software ecosystem that powers nearly every major AI framework, model checkpoint, and fine-tuning pipeline. There are still physical limitations. Even 44 gigabytes of on-chip SRAM cannot fit frontier-scale models like Llama 3405B entirely on one chip. Cerebras solves this with MemoryX and SwarmX, systems that stream model weights and distribute them across clustered machines. The bottleneck doesn't disappear, it moves somewhere else, and the entire architecture is designed around managing that trade-off efficiently. Financially, the company also depends heavily on a massive OpenAI partnership that brings both scale and risk. OpenAI is simultaneously one of Cerebras' biggest customers and a potential future competitor as it develops its own AI silicon. Meanwhile, Nvidia attacked the same problem differently, spending billions on high-speed interconnects through Mellanox instead of eliminating communication between chips entirely. Cerebras proved wafer-scale AI works. Now it must compete against the company that already dominates the entire AI ecosystem.